On your screen, you see the portrait of the legendary Hungarian mathematician Paul Erdős. Paul Erdős was one of the most prolific problem solvers of the 20th centuries. Unlike many mathematicians who are famous for grand theories, Paul Erdős is more famous for the sheer range of problems he has solved. And not only that, many of the techniques he has used are so elementary and simple that you can probably explain such techniques to an ambitious student in 9th standard or even 10th standard or something, a very young student. So I'm going to present one of the most beautiful facts in mathematics, that summation 1 by Pn diverges. Okay, Pn stands for the nth prime number. The nth prime number. Okay, this is actually an infinite series. There are infinitely many primes, and the proof of that is one of the most beautiful proofs in mathematics. I am sure you're familiar with that proof, so I'm not going to repeat it. This says that if you take the reciprocals of the primes, you get a series that is divergent. Okay. In fact, I'm not going to assume that there are infinitely many primes in this proof. The proof presented by Erdős will have a corollary that there are infinitely many primes. So let's see this proof. So let me just scroll down. Let's start the proof. What we are going to do is, it's going to be a proof by contradiction. Suppose summation 1 by Pn converges. Not P power n, Pn converges. Okay. Now, of course, here I have to make a remark. If this series turns out to be finite, I'm taking it to be convergent. I'm just extending the series by zeros, let's say. Okay. So suppose summation 1 by Pn converges. Then we can find k in the natural numbers such that summation n running from k plus 1 to infinity 1 by Pn is less than half. The tail of a convergent series can be made as small as you desire. That's all I'm using here. Okay. Now let's divide the collection of primes into two sets. We say P1 to Pk are small primes. Pk plus 1 to ... are large primes. Let's call them big primes. That sounds better. Are big primes. So I have divided the collection of primes into two parts. The first k primes are called small. Beyond that, they are called big primes. Okay. Now I need to use one fact from very basic number theory, which you have no doubt learnt in school. Any natural number higher than 1 or greater than 1 is either prime or a product of primes. This is called the fundamental theorem of arithmetic. Product of primes. This is one of the most foundational facts of number theory. So fix the natural number n, capital N. We are going to classify numbers 1 less than or equal to n less than or equal to capital N into two types. Okay, I'm going to call these two sets S, which are n 1 less than or equal to n less than capital N, such that n is not divisible by any big prime. That means from the fundamental theorem of arithmetic that I have stated above, this small n is going to be a product of primes. None of those primes can be a big prime. That's what this means. Then I'm going to call the set B again 1 less than or equal to n less than or equal to capital N, such that n is divisible by some big prime. So we have classified all the numbers 1 less than or equal to n less than or equal to capital N into these two sets S and B. Just pause the video for a moment and think about where the number 1 falls into this classification. I hope you got that. 1 is actually an element of S, simply because it is not divisible by any big prime. In fact, it is not divisible by any prime at all. Okay, now it is clear that if I call Ns the number of elements of S and Nb the number of elements of B, then a moment's thought should convince you that N is Ns plus Nb after all. Right? Now what I'm going to do is we are going to prove that if capital N is very large, how large that is, well, we will see in a moment. If capital N is very large, then N is in fact greater than Ns plus Nb, which is nonsense. Okay. How are we going to show this? Well, we deal with each case separately. Let's look at Nb. Let's try to see whether we can count Nb. So take an element small n in the set B. Take a small n in B. Then if you think for a moment, it's going to look something like this. Some prime is going to divide it. Let's say Pi. So I greater than or equal to k plus 1 is going to divide it. Recall that k was the number. P1 to Pk are the small primes. So some Pi, I greater than or equal to k plus 1 is going to divide it. So this number n is going to look like some QPi. Okay. And obviously this Q is less than or equal to capital N by Pi. Right. So because the elements of the set B are all less than or equal to capital N, it's obvious that this quotient Q has to be less than or equal to N by Pi. Otherwise, Pi into Q will be greater than N, which is not possible. Okay. So what we are going to do is, in other words, each element in the set B is some QPi, I greater than or equal to k plus 1, q less than or equal to n by Pi. For a fixed I, there are exactly integer part of n by Pi numbers in B that are divisible by Pi. Okay, what I'm trying to say here is this integer part of n by Pi just strips away the decimal portion. This capital N need not be divisible by Pi. So if I get, let's say 4.7, I'm just going to treat it as 4. That's what this integer part of n by Pi means. So what I'm trying to say is, look at all those numbers in the set B that are divisible by Pi. What are they going to be? They're going to be Pi, 2Pi, 3Pi, dot, all the way up until you reach a number QPi such that Q plus 1 Pi exceeds capital N. And how do I get what this QPi is? I precisely take integer part of n by Pi, right? That will precisely capture what this final QPi is going to be, which is just less than or equal to capital N. Okay. So this will count all those numbers that are divisible by Pi. Now do this for every prime and you will understand that this NB has certainly got to be less than or equal to integer part of n by pi summation I running from k plus 1 to infinity. Okay, right? Simply because each such term will count the number of numbers that are divisible by that particular pi. I just sum it across all the big primes. Now, immediately from our assumption that these big primes were chosen so that summation 1 by pn is less than half, what we get is this is less than or equal to or strictly less than n by 2. This is strictly less than n by 2. Okay, so nb is less than capital N by 2. That's very nice. Now let's try to estimate ns. Okay, the number of number of numbers that are divisible by exclusively by small primes. Okay, recall there are k of them, p1 to pk. There are p1 to pk. Now take a number n in the set S. Again, you can write it as a product of primes. Now what I'm going to do is I'm going to group together all those primes that are occurring exactly once in the prime factorization. That means the non-squares. So what I'm going to do is I'm going to write n as some a b squared. Okay, so these are the square part, these are the square part, and these are the square free part. Okay, so for a concrete illustration, if n1 was just p1 squared, p2 cube, p3, p4, then this will be written as p3, p4, p2, p1, p2 the whole square. Okay, so this is the square free part, this is the square free part, and this is the square part. Okay, so I'm going to club together all those primes that occur at least twice together, not at least twice. I'm going to club together all the squares together. There might be some leftover powers, like for instance here the number p2, even though it occurred as a cube, this p2 is left over. So I'm going to gather together all the squares and call it b squared, and the rest of the parts, which each prime will occur only once, will be called a. Okay, now what I'm going to do is I'm going to count the possibilities for a and b. Okay, now first observation is that there are only square root of n possibilities for b, right? Because if b were to exceed square root of n, then b squared will exceed n, which is simply not possible because this small n is less than or equal to capital N. That's the reason, right? So the number of possibilities for this number b, there are square root of n possibilities. What about a? How many possibilities are there? Well, they are just going to take some subset. So what is a? A is going to be product of primes from p1 to pk, right? Product of primes from p1 to pk. But you should take each prime only once. Each prime you should take only once. So what you can do is a you can write as p1 power x1, p2 power x2, pk power x2, xk, pk power xk, where x1, x2, xk are either 1 or 0, right? So these are all the possible a's. They are constituted by primes coming from p1 to pk, but the powers cannot be higher than 2, simply because these are the square free part. If there was a power higher than 2, then that wouldn't even occur here. So this is going to be all those p1 power x1, p2 power x2, pk power xk, where x1 to xk are all 1 or 0. And there are precisely 2 power k possibilities. That means there are 2 power k possibilities. For each p1, p2, I have 2 choices, 1 or 0. So multiplying all together, there are 2 power k possibilities. So there are at most 2 power k root n possibilities for n. Possibilities for small n, right? There are 2 power k possibilities for the number a, and there are square root of n possibilities for b. Therefore, put together, there can be only 2 power k root n possibilities for n. In other words, this argument shows that ns is less than or equal to 2 power k square root of n. Now, how does this help? Well, we have full flexibility of the choice of n. K is fixed. K is fixed because we have fixed k to be the the k to be the number such that the sum of the primes greater than pk, sum of the reciprocals of primes greater than pk is going to be less than half. That's how we fix k. K is fixed, but n is completely up to us. All we want is to find n such that 2 power k root n is strictly less than n by 2. Okay, then we will get a contradiction. In other words, we just want 2 power k plus 1 to be less than square root of n, right? Which is certainly doable. For large enough n, it will be doable. Which is certainly doable. Which means for large capital N, ns plus nb is less than n by 2 plus n by 2, which is equal to n, which is nonsense. So this completes the proof of the fact that summation 1 by p diverges. If you carefully look through the proof, we have not used the assumption that there are infinitely many primes. So as a corollary, we get there are infinitely many primes. So this is the hardest example in this course actually. This example is somewhat different from all the others that we have seen in the chapter on series. I just wanted to show this proof because it illustrates some deep thinking that can go into proving something as simple as this. This is a course on real analysis, and you've just watched a module on the sum of the reciprocals of primes is divergent.